Let us start by reminding what we did. Okay, so recall that we did these things. So first we had Fermat's theorem. Okay, so this says that if you are looking for minima maxima points, they are among the points where the derivative vanishes. Okay, so so we have f differentiable on, say, A, B, and f of c is a local minimum or maximum. Okay, so then f prime c is equal to 0. Okay, so we check this by writing the usual Newton quotient. And then using this, we had what is called Rolle's theorem. So here f is a continuous function on AB, differentiable on the inside at least, and f of A is f of B. So the function starts at a value, does whatever it likes, and then returns to the same value. Okay, so then there is a point, there is at least one point C where f prime c is equal to 0. Okay, so the rumor has it that Rolle proved this only for polynomials. He didn't accept any other function. Again, this is a rumor. He didn't accept any other function than polynomials, but then today we use this for all differentiable functions. And then we have finally the mean value theorem. Okay, so this is the big thing, the mean value theorem. Okay, so the same thing, f continuous on AB, differentiable on the inside. Okay, then there is at least one point C in AB such that the slope of the second line, B minus A, is equal to slope of the function at that point. Okay, so we proved this using this, we proved this using this. Okay, so this is what we had. Okay, now we come to something new. Okay, so now suppose f is differentiable on A, B, and f prime x is equal to 0 on A, B. Okay, so I can also take closed interval here, but doesn't matter. Okay. If the derivative is always 0, then we expect this function to be constant. And we have to check that our algebraic mechanism, algebraic machinery agrees with our expectation. Okay, so then f is constant on A, B. Okay, so what we do is let us look at the proof of this to check if the mechanism, machinery we are developing agrees with our expectation. So we take 2 points, arbitrary 2 points, and check if the values are the same. Okay, take any 2 points, say x1 less than x2 in A, B. Okay, so it doesn't matter whichever one is smaller. Okay, so we want to show that f of x1 is equal to f of x2. Okay, we want to check if f of x1 is equal to f of x2. Okay, use mean value theorem. Okay, so that's there is a point. So all we need here is these things different. There is a point C between x1 and x2 such that f of x2, so let us follow the formalism of mean value theorem, x1 over x2 minus x1 is equal to f prime c. Okay? But our assumption is that wherever you calculate f prime, you'll get 0. Okay, so this is equal to 0, our assumption. Okay, so this is different than 0. Okay, so this is different than 0, so this part makes sense. So this implies that f of x2 minus f of x1 is 0 as expected. Okay, so in real values, this is not very surprising, but later on, when you take complex values, complex functions, it is surprising. The same result holds there, but then it is surprising because with complexes, the derivative is a little bit different. Okay, so this is very simple, but it's going to be useful for us later on. Okay, so a corollary of this, useful corollary. So basically, roughly speaking, let us skip the part that they have to be differentiable, etc. So if two functions are such that their derivatives are the same, then they differ by a constant. Okay, so we wrote this in the style of Euclid. No formulas, no symbols in the statements. Everything is in words. Okay, so later on we will use this in crucially. So this is also one of the important starting points of differential equations. Okay, when we do integration, so we will keep saying plus c, so that plus c comes from here. Okay, so this means that now let us go back to the style of today's calculus. So if f prime equals g prime, then f is equal to g plus a constant. Okay. So why is this? Because you look at the function f minus g. Okay. If you look at the function f minus g, its derivative is 0, so it's constant. Okay, so as we said, it's constant. At every point, it takes the same value. Okay, so I think these are the technical tools that we will use. Okay, so you see everything starts with some simple thing like this. You expect, so this was actually Fermat's observation that if you have a minima and maxima, at that point the tangent line is horizontal. Okay, so at that time they didn't have the formalism of derivatives and other things, but the concept was there. So it was Newton and Leipzig who formalized these things. Okay, so as an application of this, for example, if f is such that f prime x is c for all x in some interval a, b. So f is differentiable there. F prime is this. Okay, so what do you expect f to be? Okay, so you take something, you take its derivative, you get constant. So that something must be c times x. Okay, so consider then f of x is equal to cx plus another k, okay? K is another constant. Okay? So how do you convince others that this expectation is true? You consider this function minus this function, okay? So to convince others, consider, show them f of x minus cx. Okay, so this is the function, say h of x. Then h prime x is equal to f prime x minus c. F prime is always c, so this is c minus c equals 0. So h of x is k, a constant. Okay, so that's precisely what you wanted to show. Okay, then from here, okay, you see that f of x minus cx equals k, and this gives you, or rather this shows the others that you are right. You had this thing. Okay, so the idea is not to get panic. You look at, first in your mind, you convince others without using any techniques. Okay, so this is also what happens in sports. When you are training, your coach always stops you and forces you to do the right movement. Okay, when you are actually going to a competition, your coach comes to you and says, forget everything I taught you, now go and win this game. Okay, so that's what you do in your life, in mathematics. First, in your mind, you win the game. Okay, forget everything you learned. What do you expect the correct answer be? And then, in order to convince others, you go through these formal things. In your mind, you don't think with these formal things. These are to convince others. Okay, so let's as an application of these things, let us show that a real polynomial of degree n has at most n roots. Okay, so let me do it here. Okay, so show that a real polynomial of degree n has at most n roots. Okay. Now, real polynomial of degree n means the following thing. Your polynomial, let us call it f of x, is an xn plus an minus 1 xn minus 1 plus a0. Here an minus 1, a0 are real numbers. Okay, so this real comes from there. Okay, and an is different than 0, and that corresponds to degree n. X to the n appears there. Okay, because you can always write such an expression. If an is 0, again you have an expression. Okay, but then you cannot put your finger here and say that this n appears. Okay, if this is 0, it doesn't appear. So when you say degree n, this is what you mean. You have real coefficients. Okay, so later on you'll learn that there is also a complex word. Those coefficients can be complex numbers. A complex polynomial will still have n roots, at most n roots, but the proof will be totally different. Okay. And here when we say at most n roots, now you all remember from high school that a polynomial has exactly n roots counting multiplicities. Okay, here we are not counting multiplicities. Okay. So we'll say at most n roots. If let's check. Okay, so how do you approach to prove this? How do you know that a polynomial has at most n roots? Okay, of course, you can write a polynomial which doesn't have any root, so that doesn't exclude it. Okay, we can write a polynomial which has n roots. Okay, so can we write a polynomial of degree n which has n plus 1 roots? We know that we cannot do this. Okay, but now is the time to think why we cannot do it. Okay, so let's, as a game, let us pull this thing into the region of the theorems that we are doing. So let us look at these theorems. We have Rolle's theorem, mean value theorem. So here, the only thing that looks usable for us is this thing. Okay. So if f of a and f of b are 0, so if it has two roots, okay, so in between the derivative will have a root. Okay, so the derivative is a polynomial of degree n minus 1. If we knew that a polynomial of degree n minus 1 had at most n minus 1 roots, then we will be done. Okay, so we play the same game with polynomial of degree n minus 1. Okay, if it has two roots in between, its derivative will have a root. It's a polynomial of degree n minus 2. So this begs for an application of induction. Okay, so we prove this by induction. Okay, so if degree of f is equal to 1, then f of x is of the form a 1x plus a 0. Okay, so clearly, well, clearly is the most dangerous word in mathematics, but let me use it. Clearly, f has one root. Okay, so which is minus a0 over a1. Okay, so it is clear enough. Okay, an objection? Okay, now assume that a polynomial of degree n minus 1 has at most n minus 1 roots. Okay, so we don't know that, but taking this assumption, can we go to n roots? Okay. Now assume, okay, now we want to, so next we want to check if a polynomial of degree n has, okay, so can have m plus 1 roots. Okay, so suppose it has m plus 1 roots. So suppose degree of f is equal to n and has m plus 1 roots. Okay, so on the real line, we mark these, suppose root 1, root 2, etc., and up to root n plus 1. Root n and root n plus 1. Okay, so how many intervals do we have here? N intervals, right? If we had only 2 roots, we would have 1 interval. If we had only 3 roots, we would have 2 intervals. Okay, so there are n intervals of the form r k plus 1. Okay, so k equals from 1 to n. Okay. Now we apply Rolle's theorem. Okay, so Rolle's theorem says that if the function has the same value here and here, in our case that value is 0, in between there is a 0 of the derivative. Okay, so notice that f of r k equals f of r k plus 1 equals 0. These are roots. Roots of f. Okay, so there exists here C1, here we have C2, okay, and here we have, you see the indexing goes like this, so here I'll have the indexing Cn, okay. So for some Ck in Rk plus 1, we have f prime Ck equals 0. K equals from 1 to n. Okay, but if f is a polynomial of degree n, f prime is a polynomial of degree n minus 1, and we showed that it has n roots. Okay, our induction assumption was that it can have at most n minus 1 roots. That's a contradiction. Okay, so let us write this over here. Okay, so when f is a polynomial of degree n, f prime is a polynomial of degree n minus 1. Okay, so we showed that f prime has n, which is strictly larger than n minus 1 roots. Okay, induction assumption. So this this contradicts induction assumption. This contradicts induction assumption. Okay, so f can have at most n roots. Okay, so all the conditions of mathematical induction is satisfied. We checked it. We checked that the statement starts somewhere. In our case, the statement starts at 1. Okay. Then we assumed without any hesitation that it holds at n minus 1. This is not a fact. This is just an assumption. Okay. Can this assumption lead to the fact of the next degree? Okay. So it leads to the fact in the next degree. Okay, so it's just like domino pieces. We made sure that the first one will be hit, and we also made sure that if this one falls down, it will topple the next one. Okay, so all of them go down. So the statement is true. A polynomial of degree n has at most n roots. Okay, so let's see what else we have as a another thing is, so we are trying to demonstrate that such simple things can lead to non-trivial statements. Another thing is about fixed points. So let me go to fixed point stuff. Okay, so a point C is called a fixed point for a function f if f of c is equal to c. Okay. So some functions have fixed points, some functions don't have fixed points. Okay. And okay, so show that if f prime of x is never 1, then f can have at most one fixed point. Okay, so it may, in most cases, it will not have a fixed point. For example, you can say f of x equals 5 times x. Okay, so does it have a fixed point? Well, how about 0? Okay, so think of a function which doesn't have a fixed point. Well, most functions don't have fixed points, so Think about one of them. Hmm? Yeah? X? X square. How about 1? 1 square is equal to 1. 1 over 2x. 0. At 0. X plus 1. Okay, so x plus 1, well, okay, so that doesn't have a fixed point. Okay, its derivative is 1. So if you have, for example, 2x plus 1, so probably it won't have a fixed point, right? Well, maybe it does. Okay, so 2x plus 2, for example, it doesn't have a fixed point. Logarithm x doesn't have a. So a function will have a fixed point if its graph intersects the line y equals x. Do you agree, or am I just trying to fool you? Okay, so is it true f has a fixed point? So again, let me write it in the tradition of Euclid. A function has a fixed point. So Euclid will have to talk about the line y equals z. Okay, so a function has a fixed point if and only if its graph intersects intersects the graph of y equals x. Okay, so let me add one more. Intersects the graph of y equals x. Is it true? On the line y equals x, take any point. Its x coordinate and y coordinate are the same. Okay, so if this intersects the graph of y equals f of x, every point on the graph of y equals f of x is of the form x f of x. When you put them together, f of x equals x. Okay, so if this is our usual coordinate system, this is the test line y equals x. So suppose we have a function like this. This is y equals f of x. Take any point here. Okay, so this point has the coordinate x, since it is on the line y equals x. And this has the form x f of x, since it is on the line y equals f of x. Okay, so we have these two things the same. Okay, so x equals f of x, a fixed point. Okay. So let's go back to this. We want to show that a point has a fixed point. Well, a function whose derivative is never 1 can have at most one fixed point. Okay, so any ideas? Suppose this is your midterm question tomorrow. Don't expect such simple questions, but just for the sake of exercise. Okay. Mind exercise. Suppose this is 25-point worth of midterm exercise. You are dreaming, you are in heaven, and an easy midterm comes, and this is one of the questions. Okay, any ideas? Huh? Yes, louder. The camera must hear every stupid thing you say, so louder. The camera hears every stupid thing I say and registers it forever. So I wish the same for you. Say now. Huh? For the seventh time, yes, why not? Okay, so this is the question. The derivative of the function is never 1. Okay, it can take several values. The derivative may be discontinuous, also it may jump 1. Okay, later on, maybe we can look at how bad the derivative of a function can be, but now we are not entering into that. We are just assuming that the derivative is never 1. Then it can have at most one fixed point. The easiest examples we had were linear functions. Okay. If the derivative is different than 1, the easiest linear function is f of x equals 5x plus something. Okay. So it's a straight line. If it is 5x plus something, you see the slope is larger like this. Wherever you place this, it's going to intersect this line, and at that point, it will have a fixed point. Okay? Or you can have a function that goes like this. For example, take the logarithm. Okay? Then it will not have, the derivative of the logarithm is going to be 1 at 1, but even then, it doesn't hit the y equals x axis. So it doesn't have any fixed point. Okay, so this is what we are trying to show. Okay, so fixed point means we are looking for, okay, so WA is short for VR. Okay, so we are looking for x such that what?
X is equal to
F of x equals x. Okay, let's make it into a shape which agrees with these things. Okay, so the only thing I can apply here is probably this one again. Okay, or maybe this one. Which one do you like? I have 3 theorems for you. So you wake up on Wednesday at 8:40, on Fridays at 10:40, nobody is awake. What's going on here? Everybody's sleeping. Okay, so this is the same thing as f of x minus x equals 0. Or I can go on forever like this. I'm waiting for a idea from you.
Let's assume that there are 2 fixed points.
Yeah, excellent, excellent. So that comes to Rolle's theorem, right? Okay, now let's follow your ideas, friend. Your friend's idea. Okay, so every time you face a situation where you have to show that something holds, if you cannot directly show it, the next thing is you assume that it is not true and check if it leads to a contradiction or not. Okay? So let's assume, as your friend said, let's assume there are 2 fixed points, say A1 and A2 for f. Okay? Then we have this. Here we have A1. Here we have A2. Okay, then we consider this function, right? Consider the function h of x equals f of x minus x. Okay, then h of A1 is equal to 0 and h of A2 equals 0. Okay, because these are fixed points. These are fixed points for f. Okay, now what do we do? Okay, so your friend gave you a hint. Now follow your friend's hint. What is next?
Then for some c in interval a1, a2, there's h prime of c is equal to 0.
Okay, so let us write this. So this is by Rolle's theorem. There is a point C in between A1, A2, where H prime C equals 0. Okay, so what next?
Then f prime x minus 1 equals 0, but f prime x is not 1.
Okay, then f prime x minus 1 equals 0, which contradicts the assumption that f prime x is never 1. Okay? So, when you wake up, you solve problems. So tomorrow, come to the exam after you drink some coffee or tea, whichever wakes you up. Okay, so then we write, technically, we write the last sentence. Hence, so if f prime x is never 1, then f can have at most one fixed point. Okay? And you can, for example, how do you find this? This year we are not doing that, but maybe after we do a little bit more derivatives. On your calculators, for example, how do you find the fixed point of cosine x? Write any number you like, then start pushing the cosine button, okay? When you push the cosine button, well, you have to arrange it. I don't know how you, calculators work differently. So you start with an arbitrary value, calculate its cosine, you get a number. Calculate its cosine, you get another number. Keep pushing the button. After a while, the number on the screen will not change. Okay, so that's your fixed point. So that's one way of obtaining fixed points. It doesn't always work. There are conditions under which this will work. Okay, but this is one method. Okay, so what else? Okay, so let us now do finding minima, maxima problems, which probably tomorrow you may have one of these things. I haven't seen the questions yet, so that's why I can freely talk about this and that. Okay, so now let me summarize how you find minima and maxima of a function on a closed and bounded interval. Okay, then we do examples. Okay, so this is, since we are at the beginning of this subject, tomorrow don't expect anything more complicated than these. Okay, how to find mean, max of a function f of x on closed and bounded interval like this. Okay. So first find the critical points. First find the critical points in A, B on the interval. Okay, because the endpoints we'll do separately, so you don't bother what is happening to the derivative at the endpoints. Okay, so critical points means that f prime a equals 0. So let's say critical points are C1, C2, Cn. Generally, if it's an exam question, you'll get one or two of these things. Either either the derivative is 0, either f prime c I equals 0, or f prime does not exist at ci. Okay? So if the point is such that it satisfies one of these things, it's a critical point. Okay? Evaluate f at these critical points. Okay? And then evaluate f at the endpoints. Okay. Now calculus tell us that, say, minima or maxima of f on A, B is minima or maxima of these numbers, f of C1, f of Cn, f of A, f of B. Okay, so that's the power of the tools that we are using. Here, of course, if you want to do this pedantically, this says that calculate f at every point here, find the maximum. Okay, of course, this is something that we can't do, we approximate, but it's saying that using these things, it comes down to this one only. Okay, so you calculate only the value of f at these points. The maximum of this is the maximum of f here. Okay, so let's apply this to some simple problems. Here, of course, you see that there are two things to pay attention here. Okay, so let me write them here. If you just keep this in mind and blindly apply this, you may get wrong because here, this part is important. Okay, so this is just two words because what you will do is you will calculate, you will first write down the derivative of f, find its roots. Some of the roots will be here, some of the roots will be outside. You don't consider the roots outside this interval. Okay, so this is the important thing here. And you also see that we have these numbers here. Okay, they change the story. Maybe these numbers, one of these numbers is large, but if this one is larger than that, then these don't give you the maximum. Okay, so the endpoints change the outcome of such a problem. So you have to pay attention to the endpoints. Okay, endpoints are always very interesting. Next semester we'll also have, for example, power series converging on some intervals. Okay, and you have to check two intervals. And of course, if you don't check it, the problem is not finished, and you will say, well, I checked it for infinitely many points. I missed only 2 points. Why is it not accepted? Because you see the color of the thing changes by the endpoints. Okay, so let us now solve a few problems. Okay, so we have time for a few problems. So I had here some problems, so we can start. Now here for a cooked up problem, you see that the bottleneck is finding these critical points. Okay, you take the derivative of this. Okay, so maybe I write this here. So the procedure, hence, okay, so let me use some other color here. Okay, so hence the procedure is calculate f prime x. Okay, solve f prime x equals 0 on a b. Okay, so this thing I'm emphasizing is back here. You find the roots of this only in interval. Okay, so this is the actually hard part in doing calculation. Solving an equation is always difficult. Okay, so if it's an exam question or a homework question, we have to start with f prime, find a solvable equation, easy to solve equation. Then for looking at this, you write f, and that becomes a problem. Okay, so for our cases, f is generally a polynomial. F prime is a simple polynomial. Then you can find this. Okay, then evaluate f at these points, at the critical points. If the derivative does not exist, you will see it here. So I'm skipping that part. So you evaluate f at the critical points in AB and at A and B. Then find min max. Okay, so let's see. So for the first problem, we have a very simple function, f of x equals 3x squared minus 12x plus 5 on 0, 3. Okay, so you see when you take the derivative, you'll get a linear equation. The root is very simple. Okay, so f prime, so find min max. Of this function on here. Okay, so here the idea of this problem is to demonstrate this procedure. Otherwise, calculation-wise, this is trivial. Okay, so we immediately take the derivative of this. This is 6x minus 12. So this is 6x minus 2. We equate that to 0. Okay, so x equals 2 is a critical point. And we check that. So you don't write this one, but you do this in your mind. 2 is in 0, 3. Okay, so this is what goes through your mind. If this was outside, you would not bother. Okay, and the derivative is a polynomial, so the derivative exists everywhere. There is no point where the derivative does not exist. Again, this flashes in your mind for half a second. Okay. Then you go to the next part, you evaluate these things. So you evaluate f of 2, you evaluate f of 0, and you evaluate f of 3. Okay, so what is f of 2? I found minus 7. Okay, there's a minus 7. F of 0 is 5. F of 3, I found minus 4. Okay, so you find minus 4. Okay, so the procedure in calculus tells us that I only look at these 3 points, and I know the minima and maxima. Okay, so looking at these things, minimum of f on 0, 3 is minus 7 at x equals 2, and maximum of f on 0, 3 is 5 at x equals 0. Okay. Now forget about the fact that the function was very simple. The story, the message of this thing is very exciting because I didn't draw the graph of the function. I have no idea about what the graph is doing. Okay. I just applied a mechanism here, and it gives me the correct answer. Okay, so for a simple function, nobody is excited, but this is the same for any complicated function. The only bottleneck is to be able to solve this. Okay, so this is the important part. If the function is complicated, solving that will be difficult. But once that is done, then you immediately know the minima and maxima of the function without knowing what the graph looks like. So in this case, let me sketch the graph. Okay, so here the graph is something like this. Okay, so at 0, it starts from here. Then it goes down to minus 4. And then at 3, it goes up to, well, it's not a straight line. Then it goes up like this. Okay, so this is 3, this is 2, and this is 0. Okay, so this was the shape of the graph, but we didn't need to look at this. Okay, so let's stop here and take a break.